All right, let's learn surface area of pyramids and cones, section 12.3. Our objectives are to find the lateral and surface area of both the regular pyramid and the right cone and use these formulas. And our essential question, how can you find the surface area of a pyramid or a cone? All right, to start, let's get some vocabulary established. We know that pyramids are the polyhedrons with a base that has a polygon, and the lateral faces are always triangles. We have a vertex, or in other words, an apex. It's the common vertex of the lateral faces of a pyramid. So when all the lateral faces come together at that point, that's a vertex, or in other words, an apex. And we have lateral faces again in these solids, similar to the previous section. Our base edges are those where the intersection of the base and the lateral face occur. All right, then you have your regular pyramid. It's a polyhedron in which the regular polygon for the base. And then the segment joining the vertex to the center of the base is perpendicular. Super important. So this is considered the height of the pyramid. And then you have your slant height, which is different height. It's the height of the lateral face, and that's going to be the side height. So your slant height and your height of the pyramid are two different heights. All right, so let's get to know our formulas for this section. So we'll start with the lateral area and surface area of a regular pyramid. Some of our letters are a repeat from the previous formulas. So capital P is still the perimeter of the base. Capital L is still the lateral area. Capital B is still the area of the base. The only new letter we have here is the slant height, and that's noted by a lowercase scripted l. Remember, the slant height is the lateral face height, not to be confused with the pyramid's height. You have your textbook formulas versus your formula chart. Again, both will work and are similar in a lot of ways, just different order of maybe the lettering. And then our lateral area for the textbook starts with a capital L, whereas the formula chart starts with an S. And I talked about how we're going to use capital L as well off the formula chart. So just change all those lateral area formulas to start with capital L's. All right, so let's use our new formulas to find lateral and surface area of this regular hexagonal pyramid. First, let's start with the formulas. So for lateral area, we want perimeter of the base, capital P, times the slant height. And then for total surface area, we want one area of the base plus our lateral height. So for both of these, we need, lateral area. For both of these, we need a slant height, that lowercase l, which we know to be 14 as identified in our given information. We also need the parts of the base. We know that we have 6 sides. It's a hexagon, and we know that each side length is 10, so S is 10. So that allows us to figure out our perimeter, which is 60 feet. So that will be enough to plug in for our lateral area, which is going to be 60 perimeter of the base times 14 lateral slant height. So our lateral area is 420 square feet. So next we need to figure out the area of our base, and we know that our base is the shape of a regular polygon, so we need to find regular polygon on our formula chart. So we're using 1/2 times the apothem times the perimeter. And we know that the apothem is this 5 square root of 3. If we were to sketch our triangle sector by itself, we can see that 5 square root of 3 already given is the altitude of our triangle sector. So the apothem is 5 square root of 3. We plug it into our formula. We get 150 square root of 3. Plug that in over here for our formula. For surface area, so we get 150 square 3 plus 420 square feet, and that comes out to be approximately 679.808. Alright, next let's go on to our cone, finding lateral area and surface area of right cones. Again, we have a vertex or apex. It's the point that is not in the same plane as the base, also known as the apex. This is very tip of the cone. Right cone is the segment joining the vertex and the center of base is perpendicular to the base. So we know it's a right cone when this segment occurs to be perpendicular to the base. Then we have our slant height again. We have our lateral face, which is the curved portion all the way around, and then the base, which happens to be a circle. The height of the cone is again that perpendicular length or distance from the vertex to the base. And then so an oblique cone, it's the segment joining the vertex and the center of base that's not perpendicular to the base. So notice that our cone's a little bit kind of slanted, not so perpendicular, so that makes this an oblique cone. And then you have your slant height. Once again, it's the distance between the vertex and a point on the edge of the base. And then your lateral surface is all the segment that connect the vertex with points on the edge of the base. Alright, and then we have our formulas for lateral area and surface area of a right cone. And you have anytime you're dealing with a cone, you have a base that's a circle, so the radius is back in play. And then slant height, again, same as the pyramid, it's the lateral face height, scripted L. And all the other letters are the same as the formula before. So lateral surface area is going to be pi times the radius times the slant height. That's same on both the formula chart and the textbook. And then our surface area is going to be that same lateral area, which is capital L, plus the area of a single base, just one base. And that's going to be pi r squared. Alright, let's find the lateral area and surface area of this right cylinder. So let's start by identifying the two formulas we're going to use. So for lateral area, we have pi times the radius times the slant height. For total surface area, we have pi r squared plus pi times radius times slant height. So both of these require slant height, so we definitely want to look at that information. So to find our slant height, which once again is the height along the lateral face, it happens to make a right triangle, so the hypotenuse of this right triangle, with the height of the cone and the radius. So that's something we can use and leverage. So we have two lengths, so that means we can use Pythagorean theorem. So we can plug in 6 and 8 for the legs, and we're solving for L. So we get the square root of 6 squared plus 8 squared, which results in a 10. So our slant height is 10. So we now have enough information to get our lateral area. Our radius is 6, so we plug in 6, and now our slant height is 10. 10 times 6 is 60. So the exact lateral height is 60 feet squared. And the approximate is 188.496 feet squared. Now for the surface area, we already figured the lateral area, which is pi r L, we just need to figure out our pi r squared. So we can plug in 6 for the radius. That gets us 36 plus the 60, which is a result of 96 pi. Type that in, we get approximately 301.593 feet squared. So lateral area is 60 pi, or 188.496 square feet. That should say feet. The surface area is about 96 pi, or about 301.593 square feet. Alright, let's take a look at our real-life problem, the traffic cone. It can be approximated by a right cone with a radius of 5.7 inches and a height of 18 inches. Find the lateral area of the traffic cone. So we start by identifying the lateral area's formula, which is pi times the radius times the slant height. So we already know our radius, we just need to figure out our slant height. So go ahead and sketch a right triangle that can be created by the slant height with the radius of the base and the height of the cone. So we know the height is 18 based on what we're given, and the radius is 5.7, also given. And we can use Pythagorean theorem, since we're dealing with a right triangle, to figure out that missing slant height, which is the hypotenuse of the right triangle. So we can take the square root of 18 squared plus 5.7 squared, which results in a square root of 356.49. So now we can plug in all our values into our formula, which comes out to be approximately 338.103 inches squared for our traffic cone's lateral area. Alright, so let's solve this real world problem that involves a composite solid. We want the lateral and surface area. So we'll start with the lateral area of the solid. We know that's going to be a lateral area of the cone plus the lateral area of the cylinder. So write out our two formulas that are going to get added together. So pi r times the slant height plus 2 pi r times the height of the cone. We know the radius is 3, our slant height given as 5, so here's your slant height, here's your radius. And then again the radius is 3, the height of the cone, the height of the cylinder is 6. So we multiply 15 here and 36 here, that combines to be 51. Keep it in terms of pi, which is exact, so the exact lateral area is 51 pi square centimeters and approximately 160.221 square centimeters. Next we want to look at the surface area of the solid, which is going to be the lateral area of the solid plus the area of the base of the cylinder. We already figured out the lateral area, that came out to be 51 pi exactly. We just need to figure out the area of the base, which is the shape of a circle. So we can substitute the 51 pi that we already figured out previously, and then we know that pi r squared is going to be the area of the base. So we plug in the 3 for the radius, getting us 9. And 9 plus 51 is 60, which is approximately 188.496 square centimeters. So the lateral area is about 160.221 square centimeters, and the surface area is about 188.496 square centimeters. Alright, let's describe the effects of change on the surface area when we only multiply one dimension by a factor. In this case, it'll be 3/2. So working our chart, our before and after change chart, so we know that radius is 10 before the change and our lateral slant height is 26 meters. So plug that into your surface area formula, pi r squared plus pi r slant height. So 10 squared comes out to be 100. 10 times 26, 260. Add those together, get 360 pi. So what happens after we change just the radius? It will become 15 meters. So 3/2 times 10 is 15. The slant height did not change, so it kept it 26. Plug it into your formula. So pi r squared plus pi rl. So 15 squared, and then pi 15 times 26, resulting in 615 pi. So take your new divided by your old and compare. It looks like the new surface area is 41/24 times the original surface area. So for this next one, we're going to multiply all linear dimensions by 3/2. So our before values did not change. There are 10 and 26. And we'll use the same value that we already figured out for part A, which is 360 pi for our surface area. So now after the change we have 15 meters and then slant height of 39. Plug that into our formula. Our formula for surface area is pi r squared plus pi rl. So we plug in the radius, which is 15 and 2 places, and then slant height's 39. So 15 squared is 225, and then 15 times 39, add that to the 225. You get 810 pi meters squared. Now let's compare. So divide the 810 pi by 360 pi, and it looks like the original surface area compared to the new is that the new is 3/2 squared, or in other words 9/4 times the original area. And that's all for this lesson. We'll see you in class.